Okay, for this afternoon class, I'll be discussing a sample problem on the topic of designing your extraction column based on the flooding velocity. So in this problem, you're given toluene as the dispersed phase. So toluene in here being the dispersed phase means that it is your solvent, and it is being used to extract diethylamine from a dilute water solution. So the solute is diethylamine in the solvent, in the carrier solvent specifically, which is water. Now your feed, which contains diethylamine in water, is the continuous phase. Now it is to be processed in a packed tower having 1-inch fall rings at 26.7 degrees Celsius. The flow rate of the toluene is 84 cubic feet per hour, and of water solution is 56 cubic feet per hour. The physical properties of the dilute solution are, so for the aqueous continuous phase, the density, or that's the raw C, is 62.2 pound mass per cubic feet. The viscosity is 2.080 pound mass per hour per feet. And for the dispersed phase, the density is 54 pound mass per cubic feet. Now, the interfacial tension in dyne per centimeter is 25. So for this problem, you are asked to predict the flooding velocity, and using the 50% of that flooding velocity, determine the tower diameter. And if in this case, if our tower should have 5 theoretical stages, what would be the corresponding tower height? Now for letter D, this will be left for you as an exercise, an assignment, which is to be submitted in your personal drives and still to be accomplished by group. So any member in the group may submit the work as long as there is a submission for the group for this particular assignment. So again, it's just one submission for the group for this particular assignment. So what is this assignment? We interchange the continuous phase and the dispersed phase, meaning your solvent will be the one that will be your continuous phase, and your diethylamine in dilute water solution will be your dispersed phase. So it is now your feed that will be dispersed in your solvent toluene, which is the continuous phase. So that would be as an assignment. So for this problem, so you have the information here, everything in here. We will try to process what we have and determine the corresponding unknowns that are being required. So let's go to our whiteboard. Okay, so we'll start with what we can work out. So your dispersed phase is toluene, so I'd like to write it as V sub D. Okay, the volumetric flow rate, or the flow rate of your dispersed phase, is given to be 84 cubic feet per hour. Now that of the continuous phase, so V sub C, is 56 cubic feet per hour. So these are the flow rates of the continuous and the dispersed phases. So it is to be processed in a packed tower. So your packed tower has the following information. So it will be using 1-inch pal rings as the packing material, and it is to process the feed at 26.7 degrees Celsius. So for the properties, of the continuous phase, so we have rho sub C, which is 62.2 pound mass per cubic feet. What else? We have the viscosity, which is 2.080 pound mass per feet per foot per hour. And should this one is given in centipoise, should this viscosity unit is in centipoise, you need to multiply it to 2.4191 to convert it to this set of units, which is 2.080 pound mass feet per hour. Okay, then what else? Mu C, rho C. Then for the dispersed phase, we have its density to be 54 pound mass per cubic feet. And then we have the interfacial tension. So I'd like it here now to write it here. It's 25 dyne per centimeter. Okay, so I think these are all the information stated in the problem read a while ago. And these are the required information. So for letter A, it requires us to determine the flooding velocity. So flooding velocities. So meaning it's asking for the V sub C and the V sub D. Okay. Then for both phases, that is. So what would be the flooding velocity for the continuous phase and what would be the flooding velocity for the dispersed phase? We are to determine the diameter of the tower at 50% flooding conditions. Letter C, you are asked to determine the height of the tower. So that would be the Z when n theoretical is equal to 5. If your tower has 5 theoretical stages. Okay, so now we will solve for the required information. Or we will determine the required information. Solution. Now, since we are to use the flooding correlation diagram, we need to determine the value of the y-axis, or we need to know the value of the y-coordinate for our flooding correlation diagram. And using the curve, we can of course determine the x value for such y value. So for us to be able to know the y value, let me first show to you that diagram that I'm referring to. Now that's the flooding correlation diagram. We need to find this. That way we can find the x coordinate of our point after we have projected it to the right on the curve, ending on the curve, and then projecting it downwards and reading the corresponding value of the x coordinate. So we will determine the y coordinate. So for the y coordinate, these are the parameters that appeared in the set of variables that we need, or properties that we need to multiply and process together. So we have the interfacial tension divided by the density of the continuous phase. This should be raised to 0.2. Then we should have here the viscosity of the continuous phase divided by the difference in the density. Then we have the surface area per unit volume for the packed tower divided by the void fraction, which is to be raised to 1.5. Okay, so with this, we will now try to substitute the available information and get the others on the appropriate table. So for the dyne per centimeter value, so we have 25 dyne per centimeter. It has to be converted to pound mass per hour squared because dyne per centimeter is a SI set of unit, whereas your pound mass per hour squared, it's the unit used in English. And our problem is using English units. So what we'll do is the 25 here should be multiplied to, so the conversion, it's also on the slide, is 28,572. This conversion allows you to convert from dyne per centimeter to pound mass per hour squared. Now, your density, since it's already in English for the continuous phase, is 62.2. So this will be raised to zero point 0.2. Now your viscosity was already converted. So if it's in centipoise, you are to use the conversion that I place in here in the given. So if your viscosity is in centipoise, you are to multiply it with 2.4191. That way you'll get the 2.080 value. Okay? So the 2.080 will be now divided by the difference in the densities of the two. So we have 62.2. By the way, this difference is absolute difference in density minus 54. Okay, then we multiply it with A and epsilon. So let's go back to our slide and let me show to you where you get the A and the epsilon. It has to be taken from a table consisting of the, or having the packing materials to be used. Since we're using 1-inch pal rings, make this bigger. Since we're using 1-inch pal rings, this is your nominal size of 1 inch. The void fraction is 0.94, and the surface area per cubic in feet squared per cubic foot of packing material is 63. So we're going to use 63 and 0.94 because we're dealing with English sets of units. So 63 for the surface area and 0.94 for the void fraction. So let's go back. So you will have here 63 divided by 0.94. And you will raise this to 1.5. The corresponding value that you will be getting here for the y is 902.8. Okay, this is the ordinate. So this is the ordinate of our point. And if we're going to use this value in the correlation diagram or curve, this one, you have to find the 902. So if this is 1,000, if this is 1,000 and this is 700, 800, 900, 902 is somewhere a little bit above this last line before 1,000. So we are to project it on the curve. So a little above there, and it will be somewhere here. This one. So approximately, if we're going to get the value here of this point, read it out in here. This one, when projected in here, will be this, and the value would be more or less around 150, 160, 170. Okay, so we will use that value. So it really depends on the one who's reading it from the graph. So let's say we're going to use the 170. So from correlation diagram or graph, your x or the abscissa is more or less 170. Okay, your abscissa is more or less 170. So this 170, based on what's seen on the diagram, should be equated on those set of parameters. Okay, let me show to you. So your set of parameters in this case will be the V sub C raised to 0.5 plus the V sub D raised to 0.5, the sum of which will be raised to 2 multiplied to rho C over A mu C. Okay, so 170 will be equated to this set of parameters. So you have to equate this one with V sub C raised to 0.5 plus V sub D raised to 0.5. This is squared multiplied to rho sub C divided by the A times the mu C. Okay? The purpose is we'll have an equation which is the V sub C and the V sub D. So if we will substitute values, so these two still being unknown, your rho sub C is 62.2, your A is 63, and your mu sub C is 2.080. You will have a V sub C, V sub D expression. This is squared equal to 357.9664. So let me check. Wait. So you have 62.2 divided by 63 divided by 2. And then we will be using it as a divisor to 170. So 358.15. And 70 times 2.080 times 63 divided by 62.2. Okay, 358. 0.14791. Okay, if you take the square root of that, your VC raised to 0.5 plus VD raised to 0.5 would be 18.92. Okay, so it's 18.92. Since it's still unknown, the two are still unknown, we can have this as equation 1. Then we can use the information provided in the given. So we can use the VC to VD flow rate ratio. So our continuous phase is 56 and your dispersed phase is 84. And then substitute the equivalent relationship in the first equation. So 56 divided by 84, that would be 0.667. So we can say V sub C is 0.667 of V sub D. Equation 2. So if we will substitute 2 to 1, so if we have 0.667 V sub D raised to 0.5 plus V sub D raised to 0.5, this should be equal to 18.92. So 18.92 in here. And we can get the square root of 0.667. We add 1. We use this as the divisor of 18.92. And then we square our answer. So you will have a V sub D value from here of 108.485. Your V sub C from equation 2 will be 0.667 of this. So 72.36. Okay. Now, this one will be your answers here of 108.45 and 72.36, though we use the ratio here in flow rates, which is cubic feet per hour. Anyway, it's dimensionless. The resulting, there's no unit left here. The units of the V sub C and the V sub D are the linear flooding velocities. So this will be feet per hour, and this one feet per hour. So this is already, so if I will label this as letter A, so this will be the answer for letter A, the flooding velocity. So we are to predict when will our column be flooded. So at these linear velocities of our dispersed phase and continuous phase, the column will be said to be flooded. So that's for your letter A. You are asked to predict the flooding velocity. For letter B, you are asked to find the diameter of the tower at 50% of this flooding velocity. So we will multiply both of this by 50. Okay, so we're now in letter B. But specifically, if I want to design my column, so remember this, if you want to design your column, you are more interested on the 50% of the flooding velocity of the continuous phase. The continuous phase. So in this case, we will multiply by 50% the continuous phase linear flooding velocity of 72.30. So in here, we will have an answer of 36.15. So feet per hour. Now we need the corresponding area. The area, that way we will have the, what we call the diameter. Now, if this is in feet per hour, what particular value will you have in mind to use? That way, you will have a corresponding unit in having the unit area. So if this is now for the continuous phase, then naturally you'll be able to find the cross-sectional area of the column where this continuous phase is passing through. I don't know. Okay, by what? So area will be the actual flow rate divided by this velocity. So I'll use C here and C here, but this one is small v, this one is big V. So our flow rate for the continuous phase is 56 cubic feet per hour. And for its linear flooding velocity at 50% of that is 36.15 feet per hour. This will give us an area which is 1.549 square feet. Now we know that area is pi d squared over 4, and as such we equate this value to this set of parameters. So your diameter for the column will be 1.404 feet. So this is the diameter of your column. Now as to the height, the Z, the formula is the theoretical number of stages times the HETS. Now, where will you get the HETS? So the problem already provides us with the 5 theoretical stages. So the HETS you will be getting from a table. So the table that was shown to you in the previous meeting. So let me show to you the table. Okay, this is the table that we are to use the HETS value based on the type of tower that is being utilized in the extraction process. Now, what we're using in this problem is a pack tower. So this is the pack tower, and the range of HETS in meters is 0.4 to 1.5. So what we're going to do, we're going to get the average of this. So 0.4 and 1.5. So we go to our solution. We will multiply this to the average 0.4 plus 1.5, the average of the two. The resulting unit for this is in meters, as you could see in the table where we took it. But our unit in the problem, or the units in the problem, are in English. So there's a need for us to convert from meters to English. So we have 1 meter being equal to 3.58 feet. So that would be now in feet. And let's see. So what would be the corresponding answer here? 0.4 plus 1.5 divided by 2 times 5 times 3.58. So that would be, why is it, wait, 0.4 plus 1.5, wait class. I think I have it wrong here in the conversion. It should be 3.28. So this is in meters. So 1 meter is 3.28 feet. So we have it. Let's see again. So 0.4 plus 1.5 divided by 2 times 5 times 3.28. This is 15.58 feet. However, this only considers the theoretical number of stages. We have to account for the settling zones in our tower in the same way with the inlet nozzles. So we are to add 2 feet for the inlet nozzles and 2 feet for the settling zone. So our true height for the tower will be 15.58 plus 2 feet for the inlet zones and 2 feet for the settling zones. So your tower would be 19.58 feet tall, which will be having 5 theoretical stages. So this is how we design our extraction tower based on the theoretical number of stages and the HETS factor taken from a table, a characteristic table, and also using the flooding condition. So we're using 50% of the flooded condition of the column, unlike in gas absorption wherein we're using 60%. Okay? That's for this problem that illustrates the use of the flooding correlation diagram and the two tables where you are to get the surface area, the void fraction, and the HETS. Now let's go back to our slide. Okay, so this is our problem. Now there are problems which does not provide us with the interfacial tension. This one. Okay. You have a formula to use in finding the interfacial tension. However, the formula is having some limitations. So the equation that is provided here will only hold true if the argument of the ln function, so this is an ln function and this is its argument, is on the range of 0.0004 to zero point 0.3. If it's lower than this and if it's higher than this, you will not be able to have shall I say, an interfacial tension which is acceptable. So a value of 1, however, for this one, for the argument of the ln, will indicate a complete solution of the phases at the plate point. So meaning if it's a complete solution at the plate point, there is no separation expected of that. Now a range of interfacial tension values of 4 to 52.5 dyne per centimeter is ideal and expected for any extraction process. Now, this is the conversion that I mentioned when we were solving the problem regarding the conversion from dyne per centimeter for the viscosity to pound mass per hour squared. And the same thing, no, this one is for the interfacial tension rather, and this one is for the viscosity in centipoise to pound mass per foot per hour. Now, as the sample of how we find the interfacial tension using this particular formula, and it's easy to follow. It's a direct substitution thing to this particular formula. Please refer to this problem that could be found in John Copley's. I will not anymore discuss it in here because it will just be substitution on the formula that was shown to you. So you will have something to do. So you read from John Copley's, this particular sample problem. If you're using the Philippine edition of John Copley's, this sample problem is example 12.6-2, page 787. So since it's easy to follow, I will leave this particular problem for you to read as an assignment, an added assignment, okay? Now, in terms of the design of perforated plate or sieve tray extraction towers, let me erase the markings first. So this will be our basis, okay? We use the, shall we say, the fractional tray efficiency formula, which also are dependent, or which is also rather dependent on the tray spacing in feet, the sigma in dyne per centimeter, and the diameter in feet with the velocities in feet per second. All of the parameters here except one are having English units. The dyne per centimeter, you have to take note, was not converted to a pound mass per hour squared. So since this is empirical in nature, we have to follow the set units for the parameters that appear in the formula. So don't make the mistake of converting the interfacial tension that you see here in dyne per centimeter to pound mass per hour squared, because the rest of the parameters here have English units. Okay, so when you solve for the fractional tray efficiency of a sieve tray or a perforated plate tower, take note, very important, set units for the parameters. This is actually the same sieve trays used in distillation and gas absorption. The diameter of the holes in the sieve ranges from 0.32 to 0.64 centimeters. The open tray area, that is if you're going to add all the areas of the holes in the tray, is 15 to 25% of the entire tray area. So the smalls must then, the holes must then be small enough. That way the sum of their areas will not exceed 25% of the area of the entire tray. Now, how is the tray spaced for this perforated plate or sieve tray extraction towers? So they are spaced from 10 to 25 centimeters. So it could be as as near each other as 10 centimeter or as distant from each other as much as 25 centimeter as to the spacing of the trays. Okay, now we proceed. For perforated substrate towers, the maximum capacity is 30 to 50 cubic meter per meter squared per hour. It has good efficiency due to minimum back mixing, and multiple interfaces can be a problem to consider here. It has limited turn down flexibility, so meaning you cannot adjust the ratio of the output to the input, that is the ratio of the product withdrawn to the feed that is being processed. It's limited, and it is affected by changes in wetting characteristics, meaning if there is not enough wetting of the shall we say, the packing material inside your plate, perforated plate or sieve tray tower, then the efficiency of removal will be greatly affected by that. So affected by changes in wetting characteristics. So limited as to which phase can be dispersed. In this case, in this particular extraction tower, if the solvent is for the dispersed phase or will be the one that will be dispersed against the flowing continuous feed phase, we cannot interchange it as like we make the solvent as the continuous phase and the feed as the dispersed phase. So whatever is the designed dispersed phase for this particular type of tower, that would be it. So it's not as flexible as the other towers in which you can exchange which of the phases will be dispersed. So it could be the solvent or the feed. Now here's a sample problem on the finding of the tray efficiency for a perforated tray tower, and this is also by nature direct substitution to the formula that I have discussed here. So I will leave this also to you to read. This is available in John Copley's. So let me check on what particular sample problem this is found. Okay. This is not the exact sample problem that is available in John Copley's, but I will end here, but you can have a similar sample problem similar to example 12.6-3. This is in page 789. So it's similar to this particular sample problem found in page 789 of John Copley's, but this was also actually taken from John Copley's. That way, we will deviate from the actual exact example on this particular concept discussed in the book. So you will have two problems to read to complement with the one that I saw regarding the design of your extraction tower, two sample problems. This 12.63, 6-3, and the other one I think is 12.6-2 in determining the interfacial tension if the problem does not provide for it. Okay, so we will continue this next meeting on the topic of the pulsed tower, extraction tower, and there's more to this. And we have the mechanically agitated extraction towers. And now we go to determining the number of stages for a multi-stage extraction tower. So we will be discussing this tomorrow. So I will be leaving now because in 3:30 our session will start already. So much for this now class in our SEPA.